Hello students, welcome to KlassPM. In today's class we are going to discuss about UV Visible Spectrophotometer and what is this device and how it is constructed and what is its working. All these things we will discuss in today's class. UV Visible Spectrophotometer is a device which we use for the UV Visible Spectroscopy. So what this spectrophotometer measures? It measures how much a sample absorbed the incident radiation. It measures how much absorption took place in a sample in the UV visible spectrum. So that's what it will measure, and there is three things will be there. So where I naught is the intensity of incident radiation and I is the intensity of transmitted radiation, where I by I naught is the percent transmittance, means it shows the how much absorption took place in the particular sample. That is I by I naught, which we call percent transmittance. So in the last class we already defined what is percent transmittance, how it is related to the absorbance. Now, so what are the parts are there here? So there is a source of radiation will be there, and this source of radiation either one particular wavelength it will emit or a range of wavelength it will emit based on what is the need here. Okay, based on our need we will select a source which will emit a range of radiations or a particular wavelength radiation. Okay, so for example it is giving a range of particular wavelengths. So those are going like scattered waves, and by using a slit it is sent like a beam of light, one single beam of light. So we know that whenever it comes from the source of light, what happens? It comes as a scattered waves. Okay, that all the scattered waves are put together as a single beam of light by using a slit. Next, the single beam of light of radiation of one wavelength or different wavelength sent to incident on the prism or any diffraction grating also. What it will do, the prism, the single beam of light is split into different wavelength based on the wavelength, like how prism will split WebGR all from violet to red based on their wavelength, how it will split. The same way the diffraction grating of the prism will do the wavelength. And here one more slit will be there. So what this slit will do is, for our selected sample a particular wavelength or range of wavelengths are required. So which wavelength is required? Like we need a violet, or we need indigo, we need red or blue or green. Which wavelength? Only that wavelength can be sent through the slit. So by adjusting its angle you can send among all those wavelengths which wavelength or which range of wavelength can be sent through this slit. Okay, and there is a half device mirror will be there. What it will do is it split the selected beam of light, monochromatic radiation, into two parts. It just splits that. Here one more device will be there. So that is a half mirror device. What it will do is it split the monochromatic radiation into equal intensity. Intensity will not change, just it split into two different radiations. The same monochromatic radiation sent in this way and sent in another way. Here this is a glass vessel which we call it as cuvette, okay, which we use for holding the sample or reference material to hold it. Here the cuvette is having only solvent, means no absorption takes place in the only solvent. Okay, and here the cuvette is having actual our sample. So this is called reference cuvette and this is the actual cuvette, and where we keep our sample, try to analyze and study the sample. And here the cuvette is having only solvent, so no absorption takes place here. And so let's talk about the cuvette. In the simple economical photometers, they use only cylindrical shaped cuvette, but in the sophisticated spectrophotometers in the cuvettes are using in the rectangular shape. Okay, that is the thing. The simple cuvettes are generally in the cylindrical shape, but in the sophisticated, if you see that, they use a rectangular shape. And also for the visible, for only if we are using our monochromatic radiation belongs to visible region, then we can use a simple glass cuvette, but if our monochromatic radiation belongs to the ultraviolet region, okay, then we have to use a special material for the cuvette, that is we have to use such compounds like quartz, because it is transparent for the ultraviolet radiation. So we have to use cuvettes which is made up by quartz for the UV range. For normal visible region we can use the normal glass material, that is a cuvette. Next, okay, so this splitting, whichever the splitting monochromatic radiation is happening, one is passing through this cuvette, another one is passing through this cuvette, okay. And if you here there is a electronic detector will be there, and which measures the intensity of the transmitted radiation, and there is the reading out machine will be there, which shows the graph against the transmittance. Here there is a reader which measures the absorbance. So if you observe here, this I note is there is no change in the intensity of the monochromatic radiation which is passing through the cuvette which is having only solvent, reference cuvette, which means there is no absorption took place in there. Here the cuvette is having samples, so that the intensity which is entering as I naught, but it came out as I. So there is a reduction in the intensity of incident radiation. So this reduction can be expressed either in terms of at the detect reader, either in terms of percent transmittance, which is equal to I by I naught, or you can also express in the terms of absorbance, which is expressed as I naught by I. So the readout machine detector will express the absorbance either in terms of percent transmittance or in the terms of absorbance. If it is percent transmittance, incident radiation by intensity of the transmitted radiation. This is the way it will measure. This is the way the photospectrometer of UV and the visible spectrophotometer works. And one more thing is that if there is no any absorbance takes place in the cuvette sample, no absorption. If no absorption takes place, what happens? Then I is equal to I naught. If absorption takes place, then I will be less than I naught. If 100% absorption takes place, already discussed in the last class, if 100% absorption takes place, then transmittance will be 0 and absorbance will be infinite. So generally the normal photospectrometers measures the absorbance between 0 to 2. Absorbance between 0 to 2. 0 to 2 means in the terms of transmittance is from 100 to 1% transmittance. From the previous class we learned that the relation between absorbance and transmittance. We will get our results either in terms of absorbance or in terms of transmittance. If it is absorbance, it is I naught by I. If it is transmittance, it is I by I naught. If there is no absorbance, these I and I naught values will be same and you will get result 1. And if there is a absorbance, then I value will be less than I naught. By using UV visible spectrophotometer, we will get our results in the UV visible spectrum. We call that result as UV visible spectrum. Okay. What information do we obtain from the UV visible spectrophotometer is called UV visible spectrum, and that is nothing but a graph between absorbance and the wavelength. Okay, this absorbance can be in terms of I naught by I or I by I naught also. Either it can be percent transmittance or absorbance. So in the graph you can see the curves here. So where the peaks are showing, that is at particular that wavelength it is absorbing maximum. That sample is absorbing maximum at this wavelength. That's why it is called lambda max. So a particular compound may no need to have only one particular lambda max. It may have multiple lambda max also. So in a particular wavelength range, it can absorb the maximum radiation at 2 or more places also. So here in this graph, this particular sample is absorbing the maximum radiation at 2 different wavelengths, and these we call it as lambda max. Okay, this is what the UV visible spectrophotometer, and the information what we get from the UV visible spectrometer is the UV visible spectrum and it is nothing but a simple graph between absorbance and the wavelength. Where the maximum absorption takes place, that wavelength is called lambda max, and it can be one or multiple for a particular compound in the range of different wavelengths.